So today I'm presenting on the topic 40% plain pozzolan usage for plastering and bonding from laboratory to field practice. I'm sure people haven't heard of plain pozzolan before, and so, Chairman, if with your permission, in the course of the presentation, if somebody wants to ask something so that we can catch up, I think if you can allow for them to ask. Yeah. We want to make sure that the clay pozzolan trickles down very well. Okay. So in this topic, the key thing is clay pozzolan. We've done a lot of presentations here in this place where we have explained what clay pozzolans are. And so I will not try to go back and explain what clay pozzolans are. Okay, so by way of introduction, we all know that previous presentation we talk about climate change, which has become very topical. And because of this, many industries are trying to implement innovative studies. I mean, when you go to the automobile industry, now people are talking of electric cars. And you go to Holland in Germany, people are saying we should do bicycling a lot. And all these things are to mitigate the effect of climate change. Now, even in the fashion industry, now they are talking of sustainable fashion. What sustainable fashion means is that the clothes that we wear should have a minimum impact on the environment. And you go to the meat industry. Now the meat industry is also talking of sustainable meat consumption. So they are saying that the more meat we consume in the world, the more we contribute to climate change. It means that we generate a lot of carbon dioxide in the atmosphere. And then cement industry. Now cement is a vital material in the world. Concrete depends on cement, and all over the world, I mean, every infrastructural development has been based on cement. It's even worse in the developing countries where we consume a lot of cement. But as we continue, we realize how cement contributes to carbon dioxide emission. So these days we're talking of low carbon cement. This is a graph that is showing the concentration of carbon dioxide as against the year between 1960 and 2015. But as of 18th May, that was some few months ago, a data that was picked by these people showed that we have about 415.02 ppm of carbon dioxide concentration in the atmosphere. Now the interesting thing is that now we are all talking about climate change. Now if you see, this is a graph showing the carbon dioxide concentration as against some many years ago. Now this is 400 years. Now the zero stands for 1950. So 400 years before 1950, 350 years. So you see that from that 400 years to 1950, the concentration of carbon dioxide in the atmosphere was around 300 ppm. Now, as development and industrialization moves on, the concentration begins to rise. So we are around 415. But climate scientists are saying that if we really want to live very well without the effect of climate change, then we have to try and then bring the level, which is 415, to about 300 ppm to the atmosphere. So we have a lot of work to do. So the point is that increase in carbon dioxide concentration is a serious threat to the environment, and this has led to global warming. I mean, the melting of glaciers. When we say glaciers, they are the ice that are found in some part of the sea. The Arctic regions. So when the climate change starts to occur, the glaciers start to melt. Now when they start to melt, it increases the volume of water in the sea, and as it increases, it leads to flooding. Now this thing has been related to the causes of tsunamis and hurricanes and all kinds of tremors that happens in the world. So the cement industry has a relation to carbon dioxide concentration. Everything about climate change has got to do with carbon dioxide concentration in the atmosphere. And the cement industry has known to release carbon dioxide into the atmosphere. It is simple from this stoichiometric equation. Research has shown that 1 ton of cement that is produced generates almost about 0.8 kilogram of carbon dioxide. And it's very simple from the stoichiometric equation. Now this is limestone. Basically what we use to produce cement is limestone and it's calcium carbonate. Now when I take limestone and I burn it to produce cement, now this is what we call pitch lime, calcium oxide, and this is the carbon dioxide that is released from the production of cement. So you see that some researchers are saying that 1 ton of cement produce approximately 1 kilogram of carbon dioxide. So this is the consumption of cement and the projection to 2030. So from 1975, cement consumption was around 70 million tons, but it has risen up, and then it is projected to be over 170 million tons. So it means that cement consumption, as far as the world is developing, will keep on rising and rising. The World Council for Sustainable Development has made a statement which is so nice. They are saying that there is a global statement of ambition calling for a collaborative effort from all cement industries to reduce carbon dioxide emission by 20 to 25 by 2030. So any country that is using cement for its development, they are trying to say that we should try as much as possible to reduce our cement usage so that we can actually impact the cause of global warming. So what has been the efforts that have been made from the cement industry? Now there have been some sustainable initiative programs that is happening in the world. For example, we have what we call low carbon cement. The United Nations Environmental Program is propagating what they call eco house. In Japan, they are also propagating what they call build a house with low, easy means embodied carbon. I will explain it as we go on. Now, there's also the use of what we call chemical and mineral admixtures. Now, the chemical and mineral admixtures has been found to reduce cement content, and then you are able to actually enhance properties of concrete works. And then we also have what we call non-cementitious housing. Nowadays, some research has shown that you don't really need cement in certain projects. You can build without cement. And so people are looking at what we call ramp earth, adobe construction. There is a lady in Ghana who is doing a project like that, building with ramp earth, no cement. It's possible. And these things are being propagated because of the effect of climate change. So, with this sustainable initiative, everything about sustainable initiative is focused on what I call embodied energy. So what do I mean by embodied energy? If I take this foam, you can't take the raw material and then create a foam like that. The foam needs to go through certain processes. Now the processes that you use to produce the foam is usually backed by some form of energy. You have to heat the rubber, you have to turn the glass into something else. So all these things that goes into it to produce the foam is the embodied energy. So in actual fact, it is the energy that is used to produce a material. So you can get, for example, if I take a material, the transportation that is part of carrying the material to some place, can be factored in to be part of embodied energy. Now the point is that if I calculate embodied energy of a material, it has a direct relation with carbon dioxide. So the higher the embodied energy of a material, the higher the carbon dioxide content of the material. So I presented these things many years ago here, but I think it's still very important to show. Now the Portland Cement Association did a research where they compared concrete without admixtures, with concrete with admixtures. So if you go to the top here, you see that we have a ready mixed concrete containing about 335 kilograms of cement. Now this one too is a ready mixed concrete containing about 279 kilograms of cement. But then if you come here, they replace the content of cement with about 20% fly ash, and look, the embodied energy was less than 1.0. As compared to this one, without anything, you see the embodied energy. Don't forget, I'm saying that embodied energy is related to carbon dioxide emission. So if you realize, if you can point it out, you can see from the graph, you see that as the percentage of the replacement increase, then the embodied energy decrease. For example, at 35%, you see that the embodied energy of the material is below even 0.9. So it means that if I try to use certain form of mineral admixtures in concrete, I can bring down carbon dioxide content. So that is the point. Now the motivation of the study, I'm saying that 40% you see. You know, clay pozzolan in Ghana started from BRR. A lot of research has been done using 30% of clay pozzolan to replace cement. Now this is a work that was done in 2001 by Tim, and you see that he used mancranson, fancy, and tunnel. So that is the common type of clay that is available in this corridor. Now in this research, you realize that the best performance was around 30%. That met a certain criteria, about 32.5 class of cement. So it has been the norm. I mean, we've been using 30% of pozzolan to replace cement. So the point is that if you go to other countries, now they are talking of performance-based cement. So out of performance-based cement, they've come out with different classes of cement. You can have stucco cement, you can have masonry cement, mortar cement, grout cement, all kinds of cement. You know, so what they do is that they pick a pozzolan and then try to replace it as high as possible and pick the standard and see if it falls within the standard. When it falls within the standard, they are ready to go. Then you can use it. So this is a typical standard I picked. Now this is ASTM C91, C91. This is typically for masonry cement. Now when you come to masonry cement, I mean, forget about the fineness, the time of setting. The most important thing that is very critical is the compressive strength. So at 7 days, now we have types of masonry cement. We have type N, type S, and type M. So if I'm in the United States and I go to the shop, I want to buy cement. Now there are various categories. I can buy type N class of cement and go and use for my plastering. I can also buy type M class of cement and go and use for my plastering. So it's not only about Portland cement, there are different categories of cement. So you see that with type N, we have 7 days strength to be about 3.4 megapascals, and then 28 days strength, which is the ultimate strength from many standards, gives you 6.2. Now, my interest was on type M. So type M class at 7 days, what I look out for is to achieve a strength of about 12.4, and at 28 days, I want to achieve a strength of about 20 megapascals. So these are performance-based cements that are produced. So this is one of the motivations, because it is done somewhere. Why can't we do it here? And then again, to many years ago, when the research on clay pozzolan began, There was nothing like, even though chemical admixtures were there, but it was far-fetched in Ghana. It wasn't so much available. But these days, it is coming close to us. So the emergence of chemical admixtures and the mineral admixtures can give material engineers to formulate what I call tailor-made cement. So you can use chemical admixtures and try to change the properties of cement and produce what we call performance-based cement. And so we've realized that the best way to actually bring down cement content down is to use chemical admixtures and mineral admixtures. And that one can actually influence carbon dioxide content in cement. So the objective of this study, I have three objectives. One, to look at using 40% pozzolan to replace cement and see its performance. And then two, after doing these things in the lab, I try to apply it in the field for plastering and bonding. And then I look at the cost effectiveness and then the embodied energy of the material that I will produce. Is it really cost effective? Can I really bring down the carbon dioxide in the material produced down? So these were the materials that I use. Portland cement, normal gas 42.5 R. Then I use the clay pozzolan. We produce it in the factory. Then I sieve the pit sand. Now SNF means sulfonated naphthalene formaldehyde. It's a chemical admixture. So it is a water reducing chemical admixture. What it does is that if you are going to use high content of water in your mix, we know, every engineer or civil engineer or civil know that water content is a devil in concrete. The higher the water content, the lower the strength. So if you are able to bring down water content, it means that you can achieve higher strength. So the SNF does that. It's able to cut down water content and then achieve or enhance workability of your work. And then normal water. So these were the pictures. This is of interest. This is the SNF material that we use. So let's look at some of the properties of the material. I have Portland cement and I have clay pozzolan. Now we have the physical properties. With this kind of work, it is always important to materials engineers to look at the chemical properties, because the chemical properties give you an idea of the performance of cement. So for example, we have what we call the major contents and then the minor contents. So the major contents are the one in the rectangular box. We have the silicon dioxide, aluminum dioxide, iron dioxide, calcium oxide. Why is this so important? Now it's important because I can look at this and then calculate what I call cement minerals from this. And cement minerals can give me an idea without doing more laboratory tests that, okay, this is how the cement is going to behave when you use it. And then we have the minor oxide. The minor oxides are this: magnesium oxide, sulfate, and then combination of potassium and sodium oxide. So these are the minor minerals, and it is very critical in concrete works. So if I buy cement and I do chemical analysis on it, I'm expecting to have some minimum minor oxides. So I'm trying to highlight these things to give an idea of how important these chemicals that are identified in cement are. So for example, if I have magnesium oxide is a chemical found in cement, and if you don't get it in a very good proportion, it can actually expand your concrete and lead to a lot of cracks in your work. The same thing with sodium and then potassium oxide. We have what we call alkali silica reaction, and if you don't deal with this, it can also lead to alkali silica reaction. They are very important chemicals that when you are in the field, or if you are supervising a project and you want to have a good idea of cement, these are some of the things you can actually let them do for you. Then for the purpose of this work, is both technical and then applied. So sometimes I have to go into a little bit of technical. You know, in materials engineering, we also are interested in what we call the mineralogy of the material. Now, because the material point of interest here is pozzolan, I have to look at the minerals. Yeah, of course, this one, as a materials engineer, can give me an idea that, oh, okay, this one is going to perform very well or it's not going to perform well. So now here, the nature of everything here tells me that the material is very crystalline. When I say it's crystalline, it means that it is well arranged, and so its reactivity will be a little bit hard. But then I can't base my final conclusion on X-ray diffraction analysis. Though it's crystalline, but I have to subject it to some form of other form of analysis. I'm just trying to mention these things so that if you come across it anywhere or whatever, you can appreciate it. Okay, so these were the methods that were used for the study. Paste and mortars were prepared by replacing cement between 10 and 40%. Now, these were the labels that I gave to it. So if you see it means that you have produced a control mix. Now you have the control mix being replaced by 10% of pozzolans and 20% of it, like, and so on. You know? So we produce the paste for the certain times, and then the mortar for the strength. Then we crush it per standard practice, the ASTM C109. I did a little bit of economic analysis from the results that I've obtained from the strength results. Then I did a calculation of embodied energy. So some of the equipment that were used, these equipments are available in the civil engineering lab. So we have the flow table, we have 2-inch mortar tubes, we have the strength, that is the universal tensor machine, we have the certain time equipment, that is the ricatronics, and then some weighing scales. Now the results. So these were the mixed proportion of the mix. If I come to the mortar, the mixed proportion in grams is shown here. But the point of interest here, you can see that the water was reducing as the percentage of pozzolans were increasing. The same way as I introduced the sulfonated naphthalene formaldehyde, it also increased. It means that the pozzolan that I have used in the material is more or less very porous. So when the material is porous, it will attract more of the admixture. But don't forget that I'm trying to reduce water content to achieve a high strength. Don't also forget that when the water content is too high in a cement mix, the strength also comes down. So that is the balance I'm trying to take. And this is also the formulation for the binders. It's always important to show the masses of your mix. Sometimes you see that people present percentages, but mostly it's better to also show the masses that you've used. So these were the results of the setting time. I wasn't so much interested in setting time, but then I wanted to get an idea of the material, because setting time just give you an idea where, for example, if I talk of initial setting time, it's giving me an idea that when I add water to cement, now some form of interaction starts. When I talk of initial setting, final setting time, it means that when I added water to cement, there were some interaction between one powder material to the other powder material. So they started to bond together. Now at final setting time, if you have that idea, it means that when you are using cement in the field, you can't work on it. When you achieve the final setting time, you know, cement, you should be able to work on it. It should be workable. When you achieve the final setting time, you can't work on it. So if you are an engineer, you can know that, okay, my cement that I'm using have this final setting time, let's say 196. So if they make the mortar mix or the concrete mix and it is there for about 196 minutes, you get an idea that no, I can't rework on it. Even if they add more water to it, it's still bad. So it's very important to know your final setting time. So these were the compressive strength results. Now, the most important thing here was this line and this line. The yellow line is the 7-day strength minimum, and then the green line is the 28-day strength. Now you realize that all of them were above the 7 and the 28 days. But my interest, I was like, okay, 40% is better, it's good, because it's above the 7-day strength and it's still above the 28 days. The same way 50%. There was a reason why I didn't use 50%.
Go over this again. Yellow line.
Okay, so the yellow line is the minimum standard for the masonry cement at 7 days, which is 7 days, which is 12.4. And then the green line is the minimum strength at 28 days for masonry cement, which is 20 megapascals. But then you realize that you are achieving higher strength at 7 days, even at 40%, and the same at 28 days. Though it is lower than the control, but who cares? I mean, I'm balancing economics as against performance and whatever. Economic analysis, very important. So these were the basis for the economic analysis. Cost per kilogram or per liter or per meter cube of the material that I use. 1 kilogram of cement, I estimated it to be 0.76 Ghana cedis. 1 kilogram of pozzolan, 0.44, even though we can still bring it down. 1 liter, 0.29. 1 liter of the chemical admixture, 5 cedis. 1 meter cube of sand, 40 Ghana cedis. So when I compute these things, this is the control cost, which is giving me 514.89 Ghana cedis per meter cube, as compared to 474.45 per meter cube of CP40. So now what do we see? Cement reduction was about 18% when I applied 40% of pozzolan. So water cost too was reduced by 20%. I was reading something on LinkedIn where they were saying that now people are talking of carbon footprint. So what about water usage footprint? So this thing can also bring to the fore about water footprint. The overall cost reduction of the two was about 8%. So cement cost reduction and overall cost reduction. Embodied energy. Embodied energy calculation is a little bit dicey. I mean, you need to get a lot of data. The basic principle of embodied energy is this. The embodied energy is a summation of the coefficient of carbon material, the materials you are using, as against the masses of the material. So this is the basic principle of calculating embodied energy. Now the good thing is that in Ghana we have not developed our own database of embodied energy of materials. For example, if I take paint, there is an embodied energy for paint. If I take aggregates, crushed aggregates, there is an embodied energy for it. The good thing is that many years ago, the UK government released a big fund for University of Bath to do a database of embodied energy for materials. So all over the world, everybody picked that database for its calculation, unless the Ghana government give us money to go into the lab to develop our own database on embodied energy. So this is the data that I picked. Now the embodied energy for cement is the embodied energy coefficient for cement is 5.5 megajoules per kilogram. So if I'm producing cement, it is 5.5. But let me also state something, that embodied energy is influenced by transportation. But in this case, I picked transportation scenario from the calculation. So for example, you look at cement importation to Ghana. Where is it coming from? Cement is coming from Europe. So the distance from Europe to Ghana influence embodied energy, because they are burning energy to bring in the material to them. But then that is a little bit complex, you know, so I took it off. But I remained to the material. Now when we come to pozzo, the embodied energy of clay, baking of clay, is 3.0 megajoules per kilogram. The embodied energy of water is 0.2 megajoules per kilogram. So, and then the embodied energy of the chemical admixture, that is the high range water reducer, is about 12.0 megajoules per kilogram. So if I do the calculation based on this embodied energy and the masses of the material, now the masses of the material is per meter cube. You know, so if I do it, now this is what I'm achieving. So the embodied energy for the control, that is the mortar mix without the pozzolan, was giving me 3,198.33 megajoules. And the embodied energy of tools of the one that I use 40% to replace is giving me 2,601.42 megajoules. But don't forget, I have stated that embodied energy has a direct relation with carbon dioxide emission. So the higher the embodied energy, the higher the carbon dioxide emission. So of course you can see from this table that it is very good to introduce the pozzolans into your material because the embodied energy comes down. So we will see that the embodied energy reduction between the two was about 16%, which is very good. Many years ago, I mean, a president in the United States were trying to even bring down the embodied energy of coal in the US to about 1%. And they were saying that if they reduce it by 1%, it's going to be very healthy for the Americans. So if you can do something to reduce the embodied energy of the material to about 16%, then it means that you can make a good case for sustainability. So the practical application of this material, I have achieved all these things from the lab. I have to transmit it in the field. The field environment is also different. Now, in the field, this was the area that I worked with. 500 square meters. That was the area that I plastered. Now, this is how they calculate things in the field. The binder to sand, usually it is 1:7, but in the lab is a little different, 1:6. Now, the thickness of the mortar was 20 mm. Sometimes people use 14 mm, but averagely it is 20 mm. So it means that the volume of the mortar that I will be producing in the field will be 10 cubic meters if I look at the area and then the thickness. Then the content of the binder that I will use from the ratio is 1.43 meter cube. So in the field, this thing is just there, that 29 bags of cement can produce 1 meter cube of mortar. So from these things and the calculations, you can estimate the content of pozzo, which is about 40%, to be 17 bags, and then the cement content 25 bags for the work of 500 square meters. So that was the basis, and then that was how the calculation was done. Okay, so this is a video that we can appreciate from the field. Okay, so this is a field work. There, I try to do all these mixes for them, and they formulated everything, the mortar, the sand, and then the pozzo, and then everything. You know, what I did was that because I knew that 40% was okay, I contacted the factory manager and I formulated 40-60% of the pozzo cement from the factory. And then I send it to the field. So they are pouring the chemical admixture to it. The chemical admixture, I tell you, is the game changer. It changes a whole lot of things. Yeah, so this is how it was applied. Now, this is also another video when they were mixing the thing, you know, just to indicate to you that it works. It really works. So the masons were trying to mix it. The point is that, you know, in Ghana we don't use more of mechanized equipment, but if we are to use mechanized, like concrete mix for the mortar, you can easily go even up to 60%. But here the errors are a lot, so I try to limit myself to 40% because we are mixing everything on the side. So this is the plaster that I did. It came out so well. And for the first time, the mason told me that this is the first time he's working on a project. He didn't see any crack. I'm telling you, I'm not joking. He didn't see any crack in the work. And the plaster was so nice, was so good. It was cool. You know, I reduced the costs and everything, and everybody was happy to use. Okay, so that is to demonstrate to you how practical the thing is. Okay, so this is, you know, we did plastering, and then what about the bonding? Now this is the plastering work I showed a video. So this is the bonding. Now we were trying to we use the cladding to bond it using the same mix proportion, and I'm telling you, it came out very well. Now the interesting thing about this work was here. They call this one sculpture. Now sculpture in the field, they use mostly cement to do the sculpture. So the guy that was doing the sculpture, I said, listen, I'm going to reduce your cement costs. So what I'm going to do is that I'm going to bring you a cement which is not 36 Ghana cedis. I'm going to give you a cement that is about 26 Ghana cedis. Are you okay with it? So I came to the factory and formulated 1:1 for him. And then he used it for this work. This is a practical work. He used it for the sculpture work. So then he came to me, oh sir, so it means that we can do business. I said, oh yeah, we can do business. So the point is that now he is interested to use 1:1, not 40-60, but 50-50 for his sculpture work. Why sculpture? Because these are non-structural work. You don't need any kind of strength, high strength to do sculpture works. You know. So this is just to introduce to you what happened. Well, let me try to conclude. After walking you through all these things, embodied energy, cost analysis, strength, and all the practical experience that I did, these were some of the things that we can conclude on. At 40%, when you incorporate the SNF, the sulfonated naphthalene formaldehyde, the compressive strength that we achieve at 3, 7, and 20 days were 9.9, 14.3, and 24.4 megapascals. Of course, when you compare it to the standard, it is higher than the standard, so you can use it. Because before the standard comes out, they have tried and settled with their value 20. So there is nothing to repeat. So you just apply the standard. Now, the 40% usage reduced cement costs by approximately 18%, water costs by 2%, and the overall mortar costs by approximately 9%. Now, at 40% pozzolan usage, the embodied energy of the material were reduced by about 16%. So these are the 3 strong conclusions I want to bring to the fore: embodied energy, cost reduction, and then the strength of the material. Before I end, let me also take the opportunity to introduce to you. Anyway, let me do some small recommendations after. Now, these were the recommendations as I thought through the work. I said, okay, the institute can or must position herself strategically for any future takeoff for massive pozzolan usage. It seems like people within actually don't apply the material very well, but I tell you, the material really works. Recently, I was with somebody who want to come into the product massively for what they call mortar cement. So if you don't prepare our house in order, some money will slip us by. So we can also look at diversifying, not one grade of cement for every kind of work. We can look at different kind of work: masonry cement, mortar cement, tiled cement, Portland cement, cement. We can do that. It's pretty easy. We can partner people and then sell the technology to them. Before I end, let me take the opportunity to introduce to you some scheduled program we want to embark on. This is a program that I have partner a company called MC Balchimi. MC Balchimi is based in Germany. Now they have come in Ghana and have set up a chemical admixture company. So at first, when I need chemical admixture, I have to order it from China. But now I don't do the order. I just go, I call them, then they deliver me. They deliver to me. Now they have gone into the field and they've seen that there's a massive problem in the concrete industry. And they also want to introduce chemical admixtures to the Ghanaian industry. So on 22nd and 23rd, we are having a workshop at the Artisan Training Center. It's free. I think people, their registration is flowing on some platforms. You can come and then we share with you overview of concrete and these things. But you know, this work that I did, I've also done it for concrete works. I don't know, I don't mind to come back within this year to do another presentation on the concrete works, you know, if the time will give me, so that we can know what can happen in concrete work, not only on mortar. I've applied it in concrete works and how it really performed. So on this note, I want to thank you, and then if there is any questions that we want to discuss, we can do that. Thank you.